All right, we're going to pick up on this. We'll pick up with problem 22, looking at this reaction, and we see that the reaction is first order in A going forward there. A going to be as a first order. And if we initially contain only A, which plot is going to be linear over the course of the reaction? So for first order, that's going to be the LNA versus time plot is going to be the first order, I think. Moving on down here, looking at number 23, we have a buffer problem. We're mixing acetic acid and sodium acetate. And so we're going to do, I'll write this over here, we've got pH is equal to pKa plus log of the acetate ion, which is the O2CCH3 ion, over the acetic acid HCO2H. Well, that's interesting. Those are actually different compounds. So we've got some more complicated problem. It's not a simple buffer problem. So let's see what's going on here. We've got formic acid, and that's going to react with water, and it's going to form hydronium ion plus the HCO2 minus formate ion. pK for that is 3.75. And then for the this would be the acetate ion now, CH3CO2 minus. That's going to react with water, and that's going to form hydroxide ion, and it's going to form acetic acid. And the pK for that is 4.75. All right, so I think what we got to think about here, this, first of all, this is a pKa refers to that, and this pKa refers to that. So if we're thinking about the K for the first reaction, that's going to be given to us by 10 to the negative 3.75. So let's see. So K for this first reaction is going to be 1.78 times 10 to the negative. That is not right. Let's try that again. Yeah, 1.78 times 10 to the negative fifth. For the second one, we're actually, since this is the base, we're looking at the pKb, which is going to be 14 minus 4.75, so pKb here is going to be 9.25. So our K for the second equilibrium is going to be 9.75 negative raised to the power of 10. That's going to be 1.8 times 10 to the negative 10th. If we sum these up, what we see is that the first equilibrium is much more prevalent. This goes much more this way than this one does, which is going to go on. But I mean, and again, they're both going to favor the reactants. So I think that our pH value is going to be affected more by the formic acid, this one, than it is by the sodium acetate, that guy right there. So the answer comes out to be 3.15. That's a bit more complicated than I would throw at you on the final, so don't worry too much about that. All right, let's move on here to 24. KSP of strontium hydroxide. We've got the value. We want to know the pH of that, so what we're going to do is get pH is, of course, going to be 14 minus the POH. And what we're going to do is figure out the POH, because that, from the hydroxide concentration, the way we get that is strontium hydroxide's KSP expression is strontium 2 plus 2 hydroxides. KSP is going to be SR 2 plus concentration, hydroxide concentration squared. If we did a ice chart, we would have 0, we really wouldn't worry about the solid strontium hydroxide. 0, 0, plus X, plus 2X, 2X, X. So our KSP expression is 2.0 times 10 to the negative third is going to be equal to 4X cubed. That's X times 2X quantity squared, since the KSP expression is OH twice, right? So that X goes there, that 2X goes there, we square that, we get the 4X squared times that initial X, 4X cubed. So X is going to be, we've got 2 KXP 3 negative. We are going to take the, divide that by 4, and then get the cube root of that. And that gives us an X value of 0.0793. That is our hydroxide concentration. Well, no, it's not. That's actually 1/2 of our hydroxide concentration. Our hydroxide concentration is going to be 2 times that, 0.158. So our POH is going to be, I get 0.80 basically, so pH is going to be something like 13.2, which is answer D. All right, looking at 25 here, when 0.1 molar HCl added to a 10 milliliter of aqueous NaOH generates a titration curve shown in a solid line. If the same number of moles of NaOH, but initially at a volume of 20 milliliters, were titrated with the 0.10 molar HCl, which of the dashed curves would best describe the titration? So what changes the titration if we have, let's see, same number of moles? Okay, well that means the equivalence point is going to come at the same place, but it's a more dilute solution. So first of all, I would go with these ones where the equivalence points are at the same place, not the ones where the equivalence points are at a different volume. So we'll rule those out. So the question is, does dissolving the NaOH in an additional amount of liquid, is that going to increase or decrease the pH? So initially, the concentration of hydroxide will be lower, so I would think the pH would be lower here. That makes sense to me like that. Now, after we cross the endpoint, we're dealing with the excess acid. We're going to have more volume, and again, that acid's going to be more dilute, so I think the pH is going to be a little higher there, so I'm going to go with answer A for that guy. All right, 26 over here, we've got a redox reaction, and we have to classify our oxidation states. This is one of these weird ones where you're going to find that your manganese is going to be both what's getting oxidized and what's getting reduced. So over here, the MnO4 2- ion, if the oxygen's -2, then the manganese here, I think, is going to be +6, because I've got 4 times -2, that's -8, plus a +6 gives me a -2 charge overall. Now, the permanganate ion over here, MnO4-, that's for similar logic. This is going to be +7, and then the oxygens are -2 there. So again, that's +7, I'll write it down here. And then in this case, don't worry too much about the hydroxides. We'll just call those -1 generally for the whole hydroxide. We've got 2 of them, so this manganese is +2. So we have +7 going to +6, right? So MnO4- picking up an electron and going to MnO4 2-. And then we've got Mn plus 2 going to MnO4 2 minus, so we're going from plus 2 to plus 6, so we're giving off 4 electrons. So what we're going to have to do is multiply this one by 4 and this one by 1, so we wind up with 4 MnO4 minus plus MnOH 2 minus going to 5 MnO4 2 minus. So the ratio, the question is, what's the ratio of MnOH2 to MnO4 2 minus? That's going to be 1 here to 5 there, so D 1 to 5. All right, 27, we're asked to get the standard reduction potential for the reduction of permanganate ion to manganese dioxide in acidic solution. So permanganate ion is MnO4 minus, and we're going to manganese dioxide, which is this guy right here, right? And what we have to do is create a thermochemical cycle. So what we're going to do here is we're going to flip this equation, the second one, and if we do that and we sum them all up, well, let's see, that's not, so it can give it to us. Yeah, if we flip that, that's gonna, the Mn2 plus will cancel out. We'll have to balance the electrons, but the good thing about that is this will be our oxidation half reaction, right? This is our reduction half reaction. EOX, E naught is EOX plus E reduction. And so the oxidation one's going to be negative 1.23, and the reduction's 1.51. So that is going to be something like 0.28, I'm going to say, which is that answer right there. Okay, and then the current passed through a solution of metal nitrate for 153 minutes, placed out 3.92 grams of the metal. We're asked, what is the metal? The way we tackle these kind of problems is that we're going to use our 153 minutes, and we're going to convert minutes to seconds, and then we're going to note that 1.20 amps is a coulomb, not a degree C, but a coulomb per second. And then we're going to use the Faraday constant and say that 1 mole of electrons is 90, what is it, 90, let's check that number, 96,500, somewhere around that. Faraday constant, 96,485, okay. 96,485 coulombs. All right, so what we can calculate there is the moles of electrons. So let's see what we got here. 153 minutes times 60 seconds times 1.20 amps, which is a coulomb per second, divided by 96,485. That gives us that we have 0.114 moles of electrons. Now, what we're going to assume, I guess, at this point is that this, well, I guess we'll see. We're going to try some values. So the question is, how many electrons? Will we use? Well, if we know what we know about nickel, nickel's usually nickel 2 plus. Copper could either be +1 or +2. rhodium is probably +2, and barium is probably +2. So let's assume that there's 2 moles of electrons involved here. It might be copper 1, but let's assume it's the copper +2, the higher oxidation state. So looks like 2. So if I have 3.92 grams of the metal, and I have 0.114 moles of electrons, and I need, for every mole of the metal, I need 2 moles of electrons. Okay. What this should give me is the molar mass of the metal. So let's see what we get. 3.92 divided by parentheses 0.114 divided by 2 close parentheses. I get 68.8 basically, and this is grams per mole. So if we look at the periodic table, back to the formula sheet here, and take a look at our periodic table down here. Let's look at some of our possibilities. Nickel here is 58, 63. What was some of our other ones? Barium, 137. And what was the other one? Was it ruthenium? Go back and look. Rhodium. So let's look here at rhodium. Rhodium is right here at 102. Okay, so that's looking closest to copper, but actually I think looking at the answer is rhodium. I think that this 2 is wrong. We take that out, then I get twice that, which is going to be 137.6 grams per mole, so pretty close to rhodium at that point. But that's sort of the tack on that. That's a harder than usual electrochemistry problem. All right, looking at the Bohr atom here, the hydrogen atom emitting the light. So it's going from N+3 to a state N, and we could either have it go from a higher state, have it go from a lower state, have it go to a higher state, or have it go to a lower state. And so you have to sort of remember how the spacings go for those energy states in the Bohr model. And what happens is that, if we think of them instead of the circle version, if we talk about E equals 0 here, this is the continuum for it, the spacing between the states gets smaller as you go up. And I'm trying to represent that faithfully. And then eventually they all kind of run together up in what's called the continuum. So if, for example, this was our n, and then this would be n plus 1, n plus 2, n plus 3, n plus 4, n minus 1. So if we look at going from here to here, that is the original thing. Answer A would be going from here to here. Answer B would be going from here to here. So this is A, this is B. Answer C would be going from 4 to here. No, sorry, from 3 to here, right there. So that would be C. I can't really mark that out. I'll put C there. And then this one right here, this would be answer D, where we get the bigger energy jump. So that's, you kind of have to think about that model of the Bohr model. Question 30 here, which element releases the greatest amount of energy upon addition of an electron to a gas phase atom? So we're looking at electron affinity. And if you look at the arrangement of the atoms on the periodic table, you've got nitrogen's on top of phosphorus, and oxygen is on top of sulfur, right? So this is our elements on the periodic table, like so with fluorine. Fluorine's right there, rather. just to give you a reference. So we're looking for the greatest addition of energy, and the answer for this is sulfur. That sulfur has the highest electron affinity. Okay, looking at 31, this is about the photoelectric effect. We're irradiating magnesium metal with a laser. The wavelength is 400 nanometers, nothing happens. If you go below 400 nanometers down to 300 nanometers, you start seeing electrons start being ejected from the surface. So somewhere between 400 and 300, somewhere in there is the threshold wavelength or frequency below which you begin to see photoelectric effect. Now, if we use a 2-watt level laser, which means we're increasing the power, the watts or power, right? That's still going to be no change at 400. So answer D is not right. It's got to be one of the ones where nothing happens at 400, because above that frequency, the individual photons don't have enough energy. But what has happened here is that the excess energy is going to produce more electrons, but the energy of the electrons won't change. It's going to be the same energy, but there will be twice as many electrons emitted. So A is our answer. The power relates to the number of electrons that are emitted once you're emitting them. The comparison of the frequency or wavelength of the light that's impinging on it with that threshold frequency, that difference is what gives you the energy of the electrons. So A is absolutely the correct answer there. Looking at the strongest bond here, that's hydrogen fluoride. If you think about these as acids, these are all strong acids. This is weak acid, which means that the HF bond is stronger. Looking at the molecular geometry and trying to come up with the smallest bond angle here, we are looking at F3 as the answer with its trigonal pyramidal structure. The other ones are, I think, more than that. Looking at these two ions here, thinking about which ones are linear. N3 azide, 3 minus azide is a linear ion, so that's the correct one here. Trying to figure out the most stable arrangement of these atoms in formaldehyde. You've got basically you need to look at your geometries here. Is what they're trying to show. So these, in A, you've got all trigonal planar around the carbon and the nitrogen. In B, the carbon's trigonal planar, but the nitrogen is some kind of a T-shape. In C, the nitrogen looks like it's a trigonal pyramidal shape, and again in D, the nitrogen's a trigonal pyramidal shape. Well, it turns out that when you fill in the electrons here in formaldehyde, the shape is such that A is your best shape, where you've got a double bond, I guess, here between the carbon and the nitrogen. The one pairs out here, I think, is the structure they're suggesting. So they kind of gave you the skeleton structure that and asked you to figure that out. Number 36. Did I skip one? No, I didn't. 36. Looking at molecular chlorine having a smaller ionization energy than atomic chlorine. Why is that? Why is molecular? And of course, the reason for that is that when you look at the electrons in chlorine and you do the MO diagram, that electron is antibonding. And so if we look at Cl2, you've got this is sigma star, sigma star, sigma star. This is 1s, this is 2s up here. And then your two p's up here, you have sigma, pi, pi star, and sigma star. And then with Cl2, we got chlorine. That's going to give us, well, actually, chlorine, we'd have to go another level. So this is going to be the 2s. This is, well, let's just do the outermost level, 3s and 3p here. So we'll just ignore everything else below that is cancels out. So in the valence shell there, Cl2, you've got 14 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 valence electrons. So it's that pi star orbital there that's getting ionized in Cl2. So again, pretty tough practice exam there, but hopefully made you think of some concepts that'll serve you well when it comes time for the real final.